Dear Chairman, dear colleagues, first of all, I would like to thank to the organizer for giving me the opportunity to share some data with you today. It's a big honor for me to be here today. So what I'm going to tell you within the next 6 to 7 minutes is the role of transcription factor GND in cardiomyocytes in the setup of myocardial infarction. So this is should I move it? This is my disclosure slide. So GND, together with two other members, GNB and CJUN, belongs to the JUN subfamily of activator protein 1 transcription complex. And to form this functional complex, it has to normally heterodimerize with the members of other subfamily, fourth subfamily, and by forming the AP1 transcription complex, this complex then recognizes the special sequence within the promoter of several genes, and by doing so, it activates or repress the expression. So as for the role of GND and how it is activated, first of all, it can be activated either by de novo transcription or by post-translational modification. And this modification is namely a phosphorylation done by several MAP kinases like ERK and JUNK. And activated GND can participate in several cellular processes like tumor angiogenesis, cell differentiation, cell proliferation, and apoptosis. And we decided to look specifically at the expression of the role of cardiomyocyte-specific GND overexpression in myocardial infarction mouse models. So we used the alpha-MHC promoter to drive the cardiac-specific overexpression of GND. The schema of the construct you see on this slide. And here you see, and hopefully can appreciate indeed the cardiac-specific overexpression of GND, where we compared the expression of GND in several mouse tissues. And here is another way of confirmation, immunohistochemistry, showing that indeed the cardiomyocyte of transgenic mice do overexpress the GND. Then we applied those 12 weeks old male mice, both transgenic and wild type, on the ligation of the anterior descending part of the coronary artery for half an hour, followed by 24 hours of reperfusion. And as depicted on this slide, you could see that transgenic heart showed enlarged infarcts, and this was further confirmed by increased cardiac troponin level measured in the serum of both groups. Next, we'll look at the capillary density of the ischemic reperfusion using CD31 and smooth muscle actin staining, and showed that both intracoronary vessels with CD31 staining and also small arterioles with smooth muscle actin staining were decreased in the transgenic hearts. Next, we'll look at the expression on mRNA level of both members of all three members of JUN subfamily, and could show that GND was nicely overexpressed after ischemic reperfusion, whereas the expression of other two members was unchanged. Then we looked at both mRNA and protein expression of PGC1 alpha, since recently a bunch of the data came out showing the co-work of PGC1 alpha together with Jundi on regulating expression of downstream targets, and we showed that both mRNA and protein expression of PGC1 alpha was decreased in transgenic hearts. And then we looked at the expression of almost all sirtuins, both nuclear and mitochondrial, and only SIRT3, which is the mitochondrial one, its mRNA expression was significantly decreased in the transgenic hearts. Oh. So, in summary, we could show that transcription factor Jundi, when overexpressed and cardiomyocyte, accelerate myocardial infarction in ischemic reperfusion mouse model, and both PGC1 alpha and SIRT3 are involved. And here, unfortunately, I cannot get the picture. I would like to show you the cartoon, but yes. We think that, as shown before, that Jundi can itself block the expression of PGC1 alpha, then can decrease the expression of SIRT3, and SIRT3, which is known to regulate the status of mitochondrial permeability transition pore, will lead to the mitochondrial swelling followed by the cell death, and by doing so it can lead to the increased infarcts. So with this, I would like to acknowledge Professor Tom Lusher, also Dr. Montecucco, and Professor Mark from Geneva, who helped me a lot with applying the ischemia reperfusion mouse model, and all members of the Center of Molecular Cardiology and University of Zurich. And with this, I would like to stop. I thank you for your attention and would be happy to take some questions.
Excellent work. When was the time, how much time after the ischemic reperfusion did you make the measurement of the vessel density?
Well, we did it, we stick to the 24 hours of reperfusion. I could probably guess what you would like to ask, that for angiogenesis, it's a bit early time point. Although, looking at the literature, we found that angiogenesis was already changed at 36 hours after the reperfusion, which you would assume to be still quite short. But what we think may be important in our setup is that not forming of new vessels, but rather retraction of the pre-existing small vessels. And this what we think may lead to the observed increased infarct areas in transgenic hearts.
Johan?
Yeah, so if I understand correctly, so the overexpression of the gene should affect the phase of ischemia reperfusion, right? So, I mean, cellular cardiomyocyte viability, or maybe these hearts are preconditioned, like preconditioned. I mean, did you check ischemic precondition?
No, we think that in contrast to what has been published so far, the cardiomyocyte-specific Jundi, when overexpressed, it is deleterious in terms of the myocardial infarction outcome, at least applying the ischemia reperfusion mouse models. And we think that this is quite important, since the data shown before, they were done using in most of the cases, the general deleter mouse, where Jundi was deleted in every single cell. Instead, we looked at it on the different extreme, but we limited our expression of Jundi specifically to the cardiomyocytes.
But you showed that troponin is less elevated, right? We
showed that troponin nicely followed the in FOXO5, that it was also increased in the transgenic heart.
Ah, it was increased.
Yeah.
I see.
So the results of your study are somewhat provocative, because there are previous reports suggesting that the June D actually has some protective properties in the heart. So maybe it's related to the level of expression?
This can be one explanation. Another explanation is that, as I was answering the previous question, so far the most of the work done was done using the knockout, June D knockout mouse, where June D was deleted in every cell. And here you can not exclude the role of June D coming from the vessels. And here we try to separate those two things. So we show that at least when overexpressed at non-physiological level in cardiomyocyte, it is deleterious. We cannot, of course, exclude the possible protective role which may come from the June D expressed in from the vessels.
Excellent. Thank you very much.